In this video, we're going to talk about a couple of formulas that are associated with binomial distributions and binomial probabilities. These are formulas that it would be a good idea to make sure that you understand thoroughly, possibly even commit to memory, although I do believe that they will show up on your formula sheet for the exam. I don't have one in front of me, so I can't confirm that, but I do think they're on there. So the first formula that we need to talk about is how you calculate a binomial coefficient. Now, a binomial coefficient is simply the number of ways that you can arrange k successes among n observations. So in the last video, I talked about, at the very end, I said we were going to roll a die 4 times, and I wanted to know how many times we could expect to roll a 5. So k in that case is how many times we actually get a 5 out of the n observations, which would be 4. So this formula might look a little odd. Oops, wrong color. But to calculate a binomial coefficient, again, that's how you arrange k successes out of n observations. It's going to look like this, and this is notation that you probably haven't seen before, so I will explain what this means. This notation here with the n over k, it's not a fraction. This is combination notation. So we read this as n choose k, and the formula is n factorial over k factorial times n minus k factorial. Now, you might not even know what this factorial business is, so let me explain both of these things. Let's start with the factorial stuff. Whenever you see an exclamation point in a mathematical equation, it would be nice if it meant that your variable, your number, was happy, but that's not what it means. It doesn't mean n, excitedly. N factorial simply means that you take the integer n, and you do have to deal with integers here, and you multiply that integer by all of the integers less than that value down to 1. So let's say we wanted to calculate, let's do an easy one, 4 factorial. And again, that's how you read it. When you see the exclamation point, you read 4 factorial. So that means that you're taking 4, and then you're going to multiply it by 3, and then by 2, and then by 1. So I'm pretty sure that would be 24. So that's how you would find the n factorial, the k factorial, and the n minus k factorial. Now let's talk just quickly about this combination notation. Again, remember that n is the number of trials, and k is our number of successes. So let's say that we wanted to go back to my dice rolling example. We had 4 trials, and maybe I want to know what's the how many possible ways could we get 3 successes. So that would be 4 choose 3. Actually, I'm going to go ahead and do that example down here at the bottom. So if we want to calculate 4 choose 3, then that's going to be 4 factorial over 3 factorial times 4 minus 3 factorial. Just a moment ago, I calculated 4 factorial to be 24. How prescient of me. Let's see, 3 factorial would be 3 times 2 times 1, so that's 6. And then 4 minus 3, that's just 1, and 1 factorial is just 1. So then we do 24 divided by 6, and that's 4. So if we have 4 trials or 4 observations, and we want to know how many ways we could possibly get 3 successes out of those 4 trials, it turns out that there are 4 ways to do that. So that's how you calculate binomial coefficients. It's just calculating the number of successes out of however many number of trials you have. So once you know how to calculate your binomial coefficients, you can then go on to calculate your binomial probabilities. So this formula is given by this statement. It says the probability that x, remember x is your binomial random variable in this setting, so the probability that x equals k, where k is some number of successes that you're interested in, is given by the binomial coefficient that we just talked about how to calculate, times p, and again p is the probability of success raised to the k power, which would be a k, times 1 minus p, which hopefully makes sense that if p is the probability of success, then 1 minus p is the probability of failure, raised to the n minus k. And the reason this last exponent is n minus k is because if you have k successes that you're already accounting for, then you have n minus k trials left that you have to account for, and all of those trials must then be failures. So this all probably sounds a little bit confusing, especially with all that notation that you're not familiar with. So I wanted to go walk you all through an example. So it says, an engineer chooses an SRS, remember SRS stands for simple random sample, of 10 switches from a shipment of 10,000 switches. So we've got a whole bunch of switches, 10,000 of them, we're choosing only a very tiny portion of them, just 10. Suppose that 10% of the switches are bad, so we know that 10% of those 10,000 switches should end up being bad. We want to know what is the probability that no more than one switch from the SRS, remember there's only 10 switches in our SRS, what is the probability that no more than one switch from the SRS is bad? Now one of the key words you need to, or key phrases that you need to focus in on here is that it says no more than. So no more than one switch is bad. So that means we would accept 0 switches being bad or 1 switch being bad. But we don't want any more than that. We don't want 2, 3, 4, and on that many switches to be bad. So that means we need to calculate 2 different binomial probabilities here. One for 0 and one for 1. But before we do that, let's go ahead and talk real quick about confirming that this actually is a binomial setting. We need to think back to our 4 requirements. First of all, are there only 2 outcomes, success and failure? And the answer to that is yes. In this case, oddly enough, we're considering a success to be finding a bad switch. And then a failure is finding a good switch. So remember before I said don't get confused. Success doesn't necessarily mean a positive or a negative thing. It's just the outcome that you're interested in. So requirement 1 is satisfied. The second thing we need to confirm, of course I've forgotten which was number 2. Are there a fixed number of observations? And the answer to that is yes. We're only looking at 10 switches, so there's a fixed number of observations that we're going to be taking. Are all of the observations independent? Again, the answer to that will be yes. There are 10,000 switches. That's quite a lot, and we're choosing a very small proportion of those 10,000. So there's no reason to think that one of the switches that we choose being bad would influence any of the other 9 switches that we chose to also be bad. And then our last requirement is that the probability of success is the same for each observation. We can say yes to this as well, again, because we have such a large number that we are pulling from. We've got 10,000 switches that we have to choose from, and since we're only choosing 10 of them, and we know that 10% of them are bad, there's no reason to think that any one switch has a higher probability of being bad than any of the others. So we've confirmed that we have a binomial setting here, which means that we can go ahead and calculate the binomial probabilities for each of the outcomes that we're interested in. We first want to calculate the probability that x is 0, meaning that we find 0 bad switches amongst the 10 that we choose. So that means we need to go back to our binomial probability formula. And I'm cheating a little bit here. So that formula says we're going to take n, choose k, in this case n is 10, and we are choosing 0 of them. Out of the 10 switches that we have, we want 0 of them to be bad. Then we need to multiply that by the probability that any one switch is bad, which we know to be 10% or 0.1. We're going to raise that to the k power, which is 0. And then we are going to multiply that by 1 minus p. 1 minus 0.1 is 0.9. And we're going to raise that to the n minus k power. N is 10, k is 0, so we're going to do this to the 10th power. Before we calculate that, let's go ahead and set up the formula for x being equal to 1, just so you can see how this works. So this time we want to calculate the probability that we have one bad switch. We're still choosing 10 switches, but we want only one of them to be bad, so this is 10 choose 1. The probability of having a bad switch is still 0.1. K in this case is 1 instead of 0. The probability of having a good switch is still 0.9. And in this situation, since n is 10 and k is 1, 10 minus 1 is 9. Now I'm going to show you on the calculator how to actually calculate these binomial coefficients, so you don't have to use the formula every single time. But just so we get comfortable with that, let's go ahead and use the formula here, just so we can practice it a little bit. So 10 choose 0 is one binomial coefficient that we need to calculate, and then 10 choose 1 is the other one. Remember, our formula is n factorial over k factorial times n minus k factorial. So we are going to do 10 factorial over 0 factorial times 10 minus 0 factorial. Now, a nice little fact that you need to know is that 0 factorial, you might want to think that it's equal to 0, but if it was, then all sorts of hell would break loose here. So we sort of force 0 factorial to be equal to 1 so that our calculations can work out. So that means we end up with 10 factorial, and trust me, that's a huge number. You don't even want to bother multiplying it all out. If 0 factorial is 1, then we don't really need to worry about that. And 10 minus 0 is, of course, just 10, so our denominator ends up being 10 factorial as well. So, of course, there's only 1 here. 10 choose 0 is 1, which makes sense. If we have 10 observations and we want to choose 0 of them, or we want 0 successes, or in this case we want to have 0 bad switches, then there's only one possible way that that could happen, meaning that all 10 of our switches would have to be good. So hopefully it makes sense why 10 choose 0 is 1. So let's now calculate 10 choose 1. Again, we're going to do 10 factorial over 1 factorial times 10 minus 1 factorial. And now 1 factorial is just equal to 1. So just like before, we can cancel that out. 10 minus 1, of course, is 9. So we end up with 10 factorial divided by 9 factorial. I don't have a lot of room to write this out. I'll try to squeeze it down here. But let's think back to what our definition of a factorial is. If we have 10 factorial, then that means we are taking all of the integers between 10 and 1 and we're multiplying them together. So we've got 10 times 9 times 8 times 7, 6, 5, 4, 3, 2, and 1. And then in our denominator, we're doing the same thing, only we're going from 9 down to 1. So 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now you probably notice that most of these factors, in fact all of them except for 1, will cancel out. The 9s cancel, the 8s, the 7s, and so on. So everything cancels except for that 10 in the numerator, which should, again, kind of make sense. Oh, right there, right here. So our final answer is 10. 10 choose 1 is 10. And it should make sense because 10 choose 1 means we have 10 observations, and we only want 1 success out of those 10 observations. So there should be 10 different ways for that to happen. The first observation could be a success, the second observation could be a success, the third observation could be a success, and so on. Okay, so we now know what our 2 binomial coefficients are. Let's go back and plug those into our formula. Oh, and I am fresh out of room, so let me go to another slide. Okay, so here are the 2 binomial probabilities that we already had set up. We just found that 10 choose 0 is equal to 1. 0.1 to the 0 is also 1. Hopefully you know that anything raised to the 0 power is 1. So really all we need to do here is calculate what point, I'll write it this way. We just need to calculate what 0.9 to the 10th power is. And if you do that on a calculator, you get 0.3487 approximately. So about 34.87% of the time, when selecting that SRS of 10 switches out of 10,000, you would get none of them that were bad. Then the probability that 1 is bad, we can find by finding 10 choose 1, which we just calculated to be 10. Multiply that by 0.1, and then multiply that by 0.9 raised to the 9th power. And if you do that, then you get 0.3874. And so what we really need to do to answer our question completely, we need to add these 2 probabilities together to get the probability that no more than 1 switch from the SRS is bad. And when you add together the probability that no switches are bad and the probability that 1 switch is bad, you get a total probability of 0.7361. So about 70, we can expect that 73.61% of the time we would either have 0 or only 1 bad switch.